The target is a Grumman F6F-3 Hellcat, Bureau number 66237. The operational constraint is an absolute depth boundary. The aircraft rests 3,400 feet below the surface of the Pacific Ocean. At this extreme depth, the environment is defined by pitch black cold and oxygen-poor deep water, where the chemistry of the sea can slow the usual clock of decay. The recovery stakes are not about finding a missing pilot, but rather about executing an unprecedented deep water extraction to study material preservation, entirely without human diver access. The initial deposit of this airframe occurred on January 12, 1944. The fighter aircraft, wearing the fuselage training code Z11, was engaged in routine training operations about 12 miles off the coast of San Diego. The flight was piloted by Ensign Robert F. Thomas. During the mission, an initiating failure forced an immediate change in operational plans. The aircraft suffered a total loss of engine power over the open ocean. Without propulsion, returning to base was geographically impossible. A forced water landing was the only viable procedural option. The ditching sequence was executed successfully. The pilot escaped the sinking airframe uninjured and was subsequently rescued from the surface. The aircraft itself, however, slipped beneath the waves and was immediately lost to the sea. The fighter breached the surface and began a long vertical descent through the water column, falling until it reached the seabed, roughly 3,400 feet below. It settled right side up and level on the bottom. For the next 26 years, it remained undisturbed, sealed off from routine human activity and insulated from surface weather. Down there, pressure dominates, temperatures hover only a few degrees above freezing, and the water can be severely oxygen depleted. The existence and exact location of the intact airframe remained entirely unknown until an accidental sensor contact occurred on March 17, 1970. The Lockheed Deep Sea Research submersible Deep Quest was operating in the region as part of a U.S. Navy-supported deep submergence program. During its submerged transit, the submersible instruments detected a large metallic object resting on the otherwise barren seabed. Investigating a deep water anomaly requires strict procedural discipline. The submersible crew navigated their vessel toward the sonar contact to establish direct visual telemetry. Because no natural light penetrates to 3,400 feet, the crew relied entirely on the exterior lighting systems of the submersible. As they closed the distance, the illumination swept across the seafloor and the target materialized from the darkness. The visual feed revealed a structurally complete fighter aircraft. The physical evidence severely contradicted standard expectations of saltwater wreck degradation. Shallow water wrecks are typically consumed by heavy biological encrustation and severe structural decay within a matter of years. In stark contrast, this specific airframe displayed remarkably intact paint and exceptionally clear military markings. There was very little visible marine growth, and no barnacles were apparent on the exterior fuselage. The training code Z11 was distinctly visible on the tail section, providing immediate and unmistakable proof of identity. The visual confirmation meant the aircraft could be conclusively linked to the January 12, 1944 ditching event. The external inspection allowed the survey team to verify the high integrity of the outer wings and the main fuselage body. The cockpit area was remarkably clear, and interior instruments were highly visible to the external cameras. The lack of structural collapse indicated that the descent to the seafloor had not compromised the primary load-bearing sections of the aircraft. Surveying at depth meant working inside a narrow cone of light, crawling the cameras along the fuselage and wings in slow, isolated passes. Yet every pass delivered the same conclusion. This airframe had avoided the rapid corrosion and heavy growth expected in shallower water, leaving the team with a rare, coherent set of material evidence. This unprecedented level of material preservation immediately altered the institutional objective. The United States Navy recognized a unique forensic opportunity. The intact airframe offered a rare chance to study how aerospace materials respond to decades of deep water submersion. However, turning a visual survey into a physical recovery introduced massive engineering hurdles. Locating a perfectly preserved fighter was one thing, but devising a method to physically rig and lift a submerged aircraft from a depth where no human diver could survive was an entirely different engineering problem. In that training geometry, an engine failure arrives with almost no margin, a steep, high-speed descent, shrinking altitude, and open ocean ahead. With propulsion gone, the pilot could not stretch the runout to reach land. He had one workable move: convert what energy remained into a controlled glide and put the fighter onto the water. Striking the surface of the Pacific Ocean required precise handling and strict airspeed management to prevent the airframe from cartwheeling or breaking apart on impact. The pilot managed the kinetic energy bleed effectively, settling the aircraft onto the water intact. Following the successful ditching, the cockpit flooded, and the airframe began a long vertical descent to a final resting depth of 3,400 feet. On the way down, the physics tightened with every foot of depth. Water pressure increases steadily with every foot of depth. At 3,400 feet down, the external physical pressure on the aircraft is immense. This sheer force dictates a strict physical constraint on any hollow aerospace structures. Any trapped air pockets inside the wings, the fuselage, or internal compartments can compress and force thin structures to deform as the surrounding ocean pressure overwhelms their limits. Yet in this case, the survey suggested several robust systems showed little obvious crushing, and some internal fluids appeared largely intact. Rather than implying a perfect seal, the more likely story is pressure equalization through flooded spaces and sturdy component geometry, which reduced the kind of dramatic collapse engineers would normally expect. On the bottom, the wreck sat in near-freezing, low-oxygen water, conditions that slow biological activity and many corrosion pathways. However, not all materials survived this isolation. Investigators noted a sharp metallurgical split. While the primary aluminum skin looked remarkably clean, certain magnesium components had dissolved away over time. In mixed metal assemblies submerged in salt water, galvanic corrosion can drive that trade-off, stripping the more vulnerable magnesium and leaving gaps and missing fittings, even as adjacent aluminum remains unexpectedly intact. This highly specific chemical and pressure environment preserved the primary load-bearing sections of the fighter. The environmental trade-off left the overarching geometry of the wreck solid and structurally continuous. The evidence proved that the saltwater had not aggressively consumed the primary flight surfaces, yet the individual rivets and structural seams had still spent over 2 decades submerged in a freezing and pressurized saltwater bath. The environment had definitively saved the structural aluminum, but applying thousands of pounds of vertical pulling force to decades-old airframe joints remained completely unproven. At this depth, verification is camera only. No diver can go down. That single constraint turns everything that follows into a remote handling problem, from first contact to first lift. The United States Navy had to make that physical connection through the Lockheed Deep Quest, using lights, cameras, and manipulator arms as their only hands. Operating a multi-ton submersible within inches of thin aluminum introduced constant collision risk, amplified by deep currents and thruster wash. The team locked in a precise approach vector to avoid stirring dormant seabed silt, because once it lifted, visibility could collapse to zero and the operation would be blind. With no one on the bottom to make manual adjustments, the lift plan had to be executed with extreme precision from above. Standard recovery protocols usually involve divers wrapping heavy nylon straps entirely around the fuselage and wing roots to distribute the lifting load evenly. At 3,400 feet, this method was physically impossible. The submersible could not dig under the wreck or lift the aircraft to slide straps underneath it. Instead, the recovery team had to identify pre-existing, structurally sound anchor points directly accessible from above. This forced a complete reliance on remote submersible cable rigging. The engineers analyzed the high-resolution visual telemetry transmitted from the seafloor. They searched the airframe for structural voids or solid engine mounts that could support thousands of pounds of vertical tension. The detailed visual inspection revealed a critical structural opening. Decades of galvanic magnesium loss had stripped away specific components, and several cowling panels between the engine and the main cockpit were naturally missing. This exposed the heavy internal engine mounts and the primary structural frames of the Grumman fighter. The missing panels provided a crucial access point for the remote manipulators. The engineering team designated these exposed frames as the primary lifting nodes. The operation required threading heavy lifting cables completely through the existing airframe gaps. The Deep Quest submersible slowly positioned itself directly over the nose of the aircraft. Using hydraulic manipulator arms, the operator carefully guided a specialized lifting line down into the open engine cowling compartment. The mechanical claw pushed the cable through the dark void, navigating without direct line of sight past sharp aluminum edges and internal wiring. Once the lead end of the cable passed through the lower section of the exposed engine mount, the submersible repositioned itself to retrieve it. The robotic arm reached into the lower cowling gap, grasped the line, and pulled it back up to the exterior of the aircraft. This remote rigging procedure formed a continuous physical loop directly around the heavy structural frame of the fighter. Securing the lifting cable in this exact location was a calculated trade-off. The engine mounts are designed to handle immense forward torque and the sheer weight of a 2,000-pound radial engine during flight. However, they were never engineered to support the entire suspended mass of a waterlogged aircraft hanging vertically from a single point. The recovery team had no alternative. Any attempt to attach the cable to a weaker section, such as the outer wings or the tail, would induce an immediate structural tear under the stress of a deep water hoist. Before committing to the hoist, the submersible ran a final perimeter sweep, lighting the cable path to confirm nothing could slip or bite into the skin once tension came on. The make-or-break variable was alignment with the wreck's center of gravity. Off-center load would twist the aircraft the moment it lifted free. With the cables locked onto the thickest remaining structure, the operation moved from rigging to the real test, whether the deep sea winch could pull a flooded fighter off the bottom. Neutralizing live explosive hazards before bringing a fully loaded combat aircraft through the surface layer dictated a mandatory operational pause exactly 50 feet below the waves. The extraction sequence required complete mechanical control over the ascent. On the surface, the auxiliary repair dock USS White Sands positioned itself directly above the wreck site. To execute the primary vertical extraction, the ship utilized a specially designed deep-sea winch. The mechanical objective was to initiate a steady, uninterrupted lift from a depth of 3,400 feet. Hoisting the fighter was never just a question of the airframe's own weight. The long steel cable stacked enormous load onto the winch, and every roll and pitch of the surface vessel translated into tension spikes down the taut line. Those motion-driven surges could push the wire past its limits in an instant. That physical threshold was breached during the long ascent to the surface. The immense dynamic strain caused the primary lift lines to snap twice during the hoisting operation. Each failure forced the crew to re-establish rigging and regain steady control before the lift could continue, and the ascent rate was deliberately reduced to avoid another break. Once the winch resumed steady operation, the recovery team adhered strictly to a pre-planned two-stage lift protocol. After securing the weapon systems, the divers finalized the secondary surface rigging process. They secured the heavy, reinforced lifting lines required to pull the flooded airframe through the air-water interface. Once the EOD team cleared the ordnance and re-rigged the heavy lines, the Navy faced the final and most destructive hazard, the surface wave action. Pulling a submerged aircraft through the final boundary of the ocean surface dictates a critical engineering trade-off. The recovery team faced a binary choice between a traditional vertical crane lift and a buoyant capture. A standard salvage operation uses a heavy marine crane to hoist the wreckage straight out of the water and swing it over the side of a surface vessel. However, transitioning a fragile airframe from water to air strips away the buoyant support of the ocean. Once the aircraft breaches the surface, the thousands of gallons of seawater trapped inside the wings and fuselage instantly convert into unmitigated weight. If a crane pulls a flooded fighter directly into the open air, the immense internal mass will concentrate massive shear forces on the lift points, risking an immediate structural failure of the main wing spars. Furthermore, a suspended aircraft swinging on a cable over a steel deck introduces a severe risk of impact damage from the rolling motion of the ship. To bypass the structural hazard of a crane swing, the United States Navy utilized the specialized architecture of the auxiliary repair dock USS White Sands. Instead of pulling the fragile airframe up into the air, the operational plan was to manipulate the ship to capture the submerged wreckage. This required the execution of a floating dry dock extraction. The surface vessel was a floating auxiliary repair dock with a floodable dry dock basin. The crew ballasted the dock down until the stern gate and the interior docking space were submerged below the worst of the surface wave action, creating a calmer underwater entry point for the suspended aircraft. Meanwhile, the Grumman fighter remained suspended securely on its secondary surface rigging at a holding depth of 50 feet. Because the recovery team had previously established direct mechanical control over the load, they could now execute a horizontal transfer. Rather than hoisting the aircraft vertically, the surface operators utilized support vessels to begin a slow horizontal towing maneuver. The procedural objective was to move the suspended mass steadily through the upper water column and navigate it directly into the submerged chamber of the White Sands. Towing a waterlogged airframe requires absolute geometric precision. The surface operators had to align the exact center line of the suspended fighter with the narrow open gate of the dry dock. Any lateral misalignment would cause the outer wings to strike the thick steel bulkheads of the enclosure, destroying the primary material evidence instantly. Operating at minimal speed to prevent hydrodynamic drag from tearing off the external control surfaces, the team successfully maneuvered the F6F-3 Hellcat through the aft gate. They positioned the fuselage precisely over the heavy wooden deck blocks submerged below. Once the airframe was completely contained within the internal perimeter of the vessel, the recovery procedure transitioned from a dynamic towing operation to a controlled buoyant capture. The dock crew initiated a heavy deballasting sequence. High-capacity industrial pumps began ejecting hundreds of tons of seawater from the internal ballast tanks of the ship. As the tanks emptied, the entire dry dock structure slowly gained buoyancy and began to rise toward the surface. As the internal deck came up beneath the floating aircraft, the heavy landing gear struts and the structural belly settled firmly onto the supporting blocks. This extraction method changed the physics by shifting the burden from lifting to controlled dewatering. As the White Sands deballasted and rose, the deck blocks came up to meet the fuselage while the water level inside the well deck dropped inch by inch. That pacing let trapped seawater drain out through gaps and ports as buoyant support receded, bleeding weight away instead of stacking it onto 26-year-old joints. By controlling the immediate environment around the aircraft rather than forcing the aircraft through a chaotic transition zone, the Navy successfully bypassed the most dangerous phase of the extraction. The airframe never hung unsupported in the open air, and it was never subjected to the dynamic shock of a swinging hoist. The airframe was finally secure and draining on a steel deck, but the true test of the extreme preservation hypothesis was still waiting inside a naval laboratory. The extraction successfully deposited the airframe onto the steel deck of the ship, but the recovery was never intended to be a standard salvage operation. The mission was driven by strict forensic inquiry. Physical evidence recovered from the seafloor immediately validated the visual survey, yet the functional integrity of complex internal mechanisms remained completely unknown. Investigators required physical proof that the specific alloys used in standard military aviation could survive extreme hydrostatic pressure and saltwater immersion without microscopic degradation. To acquire this proof, the engineering team isolated a precise mechanical assembly for evaluation. They extracted a single .50 caliber machine gun directly from the internal wing structure of the fighter. This heavy weapon had spent over 2 decades completely flooded in salt water. To determine its true mechanical condition, the weapon was securely transported to the Naval Weapons Laboratory located in Dahlgren. Forensic protocol required the laboratory technicians to treat the recovered gun exactly as they would a standard service weapon drawn from long-term storage. They disassembled the receiver, cleaned the internal components to remove residual deep sea silt, and applied standard military lubrication. The internal springs, sears, and firing pins showed absolutely no signs of pitting, rust, or structural decay. For the final confirmation, technicians mounted the reassembled machine gun on a secure static test stand, fed in a belt of live ammunition, and engaged the firing mechanism. Reported results indicate the long submerged weapon cycled and fired about 30 rounds without a stoppage. The outcome reinforced the same lesson seen on the airframe. Cold, oxygen-poor deep water can greatly slow corrosion in some assemblies, even if it does not prevent every form of material loss across an entire airframe. Following the successful Dahlgren firing test, the scientific objectives of the United States Navy were fully satisfied. The preserved airframe had delivered the required data regarding deep sea metallurgy and material survival limits. Consequently, the Navy formally transferred custody of the wreck, shifting it from a technical test subject into a historical legacy project. The core aluminum structure remained strikingly sound, but key pieces in the engine area assembly and external coverings were gone, losses consistent with the earlier galvanic trade-off. Preparing the aircraft for permanent public display now depended on sourcing period-correct replacement materials without compromising the integrity of what the deep water had preserved. To reconstruct a fully accurate F6F-3 Hellcat, restoration crews had to source period-correct replacement materials. Manufacturing modern replica components would severely compromise the historical integrity of the airframe. Instead, the restoration team turned to a harsh operational environment to locate compatible wreckage. During the post-war era, the Navy utilized stripped-down Hellcats as remote-controlled target drones. On San Nicolas Island, the wrecks of 4 F6F-5K target drones provided a pool of compatible parts that could be salvaged for restoration. Recovery teams scavenged the dry land drone wrecks to harvest surviving structural parts. They recovered the specific cowling panels, engine components, and internal fittings required to fill the physical gaps in the deep-sea airframe. By mechanically merging the perfectly preserved deep-water aluminum with the weathered dry land components, the engineers carefully reconstructed the complete geometry of the 1944 fighter. The restoration process required strict evidence discipline to ensure the final assembly accurately reflected original manufacturing standards without erasing the physical marks of its deep-sea immersion. Since 2019, the reconstructed fighter has served as a baseline case study in deep-water aviation archaeology. The airframe is housed indoors and protected from humidity to reduce the risk of delayed corrosion in original metals. The Grumman F6F-3 Hellcat, Bureau number 66237, is displayed at the Naval Air Station Wildwood Aviation Museum as part of its public collection.